Okay, so so if you let's kind of reflect on what we did yesterday real quick, just kind of get our momentum back up again. So first thing we talked about was the idea of extrema or extrema. Okay, that's the plural of the word extremum or extremum. And basically those describe both the maximum and minimum values or locations of the values of a function. All right, so we defined f of c to be a minimum of f, so f of c is the minimum value, as we say, a minimum value if that's the lowest y value for any other y value. It could be the lowest or equal to the lowest y value, right? Same thing for a maximum. A maximum is a maximum if that c, or f of c is a maximum if f of c is greater than or equal to f of x for all x. Okay? And we looked at some situations, some variations on the function x squared plus 1. So we looked at x squared plus 1 on a closed interval from -1 to 2. All right, and we identified that both this variation of x squared plus 1 on the closed interval, it had both an absolute maximum and an absolute minimum. Okay, the absolute maximum occurred at 2, and the absolute maximum value was 5. That's the highest y value. Okay, the absolute minimum, the absolutely lowest point, right, occurred at x coordinate of 0, and its y value, the absolute minimum value is 1. Okay. Moving over to our next graph here. Now we're talking still about x squared plus 1, but now we're on an open interval. We no longer have a maximum value really because we're kind of like always approaching a certain value, but we never actually get to it. Okay. So it's not I guess when we're talking about absolute maximum values, we're talking about finite values, and I guess the 1.99999 is not a finite value, even though it is 1.999 is, or I guess in this case, 4.999 is equivalent to 5. But anyway, so the absolute maximum does not occur, but we do still have an absolute minimum value, okay, that occurs again at the x coordinate of 0, but the absolute minimum value is 1. Okay, and then last but not least here, we had a discontinuity. We kind of make this a piecewise function. We have a discontinuity at 0, so we have an absolute minimum now, we don't have an absolute minimum now, but we do have now an absolute maximum still because of the way that interval is set up. Okay, and that led us into then the extreme value theorem, which says that if f is continuous on a closed interval AB, so if f is both continuous and it's on a closed interval AB, then f must have both an absolute minimum and an absolute maximum on that interval. Okay, so again, extreme value theorem doesn't tell you how to find the absolute minimum or maximum. It just says that they must exist if f is continuous on a closed interval AB. Okay, that's it. So it's kind of like the intermediate value theorem. We don't know, intermediate value theorem. We don't know exactly where those values are going to be, but we know that if a function is continuous, it's going to hit all those y values between the endpoints of the interval. So I don't know why I didn't put a big old X there. Those are arrows. So here again, we look now at relative extrema. Relative extrema are kind of like there are a variety of extrema. Okay, a relative minimum is not the absolutely lowest point. It's the lowest point in like a neighborhood of points. So here it looks like it's like kind of you see those in a valley, okay, or a trough. Sometimes we call that. Okay. So in this case, our relative minimum occurs at 2, -4, and we have a relative maximum at 0, 0. Okay. These are not absolute maximums or absolute minimums because the graph continues to increase to infinity or to decrease to negative infinity, as we kind of move along there. Okay. And I shouldn't really say decrease negative infinity. It's increasing, but it's increasing from negative infinity. So our end behavior, okay, continues on lower and higher than our relative mins and maxes. And so we talked about then again what to look for, all right, in non-mathematical terms, peak or hill, trough or valley. And we found that when we identified our relative maximum and our relative minimum here, okay, which actually also happen to be absolute maximums and absolute minimums too, right? Because sine won't get any higher than 1, and sine won't get any lower than -1, so those are also absolute maximums and minimums too. We noticed that when we take the derivative and evaluate the derivative at the x coordinates, the derivative equals 0. And we saw last night in the homework that at any relative maximums or relative minimums, the derivative either equaled what? 0, or it was undefined. And so now we move on to page 2 finally, okay? And we're back into this, and now we're talking about the definition of a critical number. So let f be defined at c, that means f, works at c, if f prime of c equals 0, or if f prime is undefined at c, then c is a critical number of f. All right. So looking at here, this is our graph of f. In this case, I'll label that as f. All right. Where would we expect to have a critical number for f? So at the coordinate x equals 2. So we have a critical number, okay, is x equals 2. So that's a critical number. That x value, okay, that's like the c that would make our derivative equal 0. How could you tell there, Austin, that it was at 2 that happened?
Because at the x value of 2, we see that there's a point that bottoms out, therefore indicating it is the relative minimum.
Yep, it kind of bottoms out. We can also say what kind of tangent slope does it look like we would have there?
0.
Looks like our graph would have a slope of 0 there, right? And that means the derivative, right, which is the slope of our function, the derivative would have a slope of 0 right there at that instant. Okay, exactly right. Are there any other critical numbers it looks like on this graph?
No.
Does it look like the graph will have a derivative of 0 anywhere else? Yeah, no. Does it look like it's going to be undefined anywhere? No, no. All right. How about this next graph? This is also f, we'll say. Okay. Where do we have a critical number here, right?
At x equals 2.
Also at x equals 2, critical number.
Because it's pointy there, so it's undefined.
Yes, okay, so the graph of our function's pointy, right? We know that means the derivative will not exist, and so that's another possible critical number. The f prime would be undefined at 2. Okay, so that's right. Okay, those are our critical numbers are. So, go down to a theorem. Relative extrema only occur only at critical numbers. So if f has a relative minimum or a relative maximum at x equals c, then c is a critical number of f. Okay? Notice what this is not saying. C, if x equals c is a critical number of f, there is not necessarily a relative extrema at x equals c. Okay? So what I mean is, if you have a point that's a relative max or a relative minimum, a relative maximum or a relative minimum, then that point must be a critical point. Either the derivative equals 0 there or the derivative is undefined there. However, just because the derivative equals 0 or the derivative is undefined does not necessarily mean you have a relative maximum or relative minimum. All right? So again, if it's a relative maximum or a relative minimum, then that point must also be a critical point. But if something's a critical point, it doesn't have to be necessarily a relative maximum or relative minimum. And here's an example of that with x cubed. So let's do a quick sketch of what x cubed looks like. All right, so it kind of comes up like this, goes through like that, and comes up like this again, right? I didn't do a great job sketching that. Let me see here. My graphic calculator is back. The calculator probably does a better job than I do graphing this. So let's see. So calculator does a better job there of the way I sketched it. Okay. In fact, I feel like that's really sad, so maybe I'll just redo the whole thing here, right down here. Okay. It's kind of important that I sketched it more accurately than what I did there, so that's why I resketched. Okay. So, f of x has a critical value at, so that means this wants us to find the critical values of our function x cubed. So, to do that, what will we do here, Brandon?
So, look at the point of which it would be like tangent slope of 0.
Okay.
Or undefined.
How can we use our function to do that?
Take the derivative.
Take the derivative. F prime of x is 3x squared, and what should we do with our derivative?
Plug in 0.
Now plug in 0. We want to know when it equals 0. We want to know when it equals 0, right? Critical numbers occur when the derivative is 0 or when the derivative is undefined. So 3x squared equals 0 when x is what, Brandon?
0.
Yeah, 0. Exactly, yeah. So f of x has a critical value at what? X equals 0. Beautiful, that's it. Brandon, will 3x squared ever be undefined?
No.
No. So we don't have to worry about critical points from that. Okay, so we'll skip that piece of it. Okay, f of x has a relative extrema at, Drew, where do we have a relative extrema here? Do you see a hill or a valley here? Yeah, nowhere. Okay, so here's an example of that. So don't just think, oh, because I have a critical value, that critical number has to be either relative maximum or relative minimum. In this case, okay, yes, we do have the derivative equal to 0 at x equals 0, right? We have at an instant, we have a horizontal tangent line there. But that point is neither a relative maximum or a relative minimum. Okay, so yes, Brandon.
So for the relative extrema, would DNE be the acceptable answer?
Yeah, you could also say does not exist there too. Yeah, relative extrema do not exist. Again, when you can abbreviate like for homework and stuff like that, but like on tests and stuff, I would really recommend you write the phrase does not exist. Okay, and in fact, since then that's what you should do for a test, I'd also recommend then for the homework you write does not exist, not just DNE. So just because we want to practice like we're going to play. All right, questions on any of that? Feeling good? All right, let's flip it over then and look at some more. All right, so letter B here. So let's try and identify some extrema here. All right. So this is a little bit trickier to do because we really can't take the derivative and have an absolute value, but we can still kind of like think about what the derivative would be and all that here. So let's see here. Chanda, what kind of, do we have any relative extrema here? So do we have like a relative maximum, relative minimum? Okay, so why do you say no? Right, so it doesn't bottom out, which means the derivative would not equal 0, but what would the derivative be at 2? Not 0. It would not exist, right? So, because the derivative does not exist there, that's a possible critical point. So x equals 2 is a critical point of f, okay? And then since it's a critical point, it could be a relative maximum or relative minimum. In this case, Chanda, what is it? At x equals 2, this point, is that a relative maximum or a relative minimum? It's a minimum. Yeah, it is a relative minimum. Yep. It's a relative minimum.
Would it not also be the absolute minimum?
Yes. So excellent point there. Yes. So it's a relative minimum at x equals 2, but because that is the absolutely lowest point, it's also the absolute minimum.
So do we have to refer to it as both, or does absolute trump relative, I guess?
You will be asked for them separately. So sometimes you'll only be asked for relative extrema, sometimes you'll be asked only for absolute extrema. So it really depends what you're asked for. I'm going to give them both here because just for the thoroughness of your notes and things. Okay. What about maximum values here? So like Connor, do we have a maximum, a relative maximum here, for example? Right, and so then we don't have a relative max. And so do we have an absolute max then too? No, no absolute maximum either. Yeah, so no relative maximum or absolute maximum. Okay. And I know you guys may be abbreviating in your notes. Instead of writing the word maximum, you may be writing just the word max, and that's okay, but for a test, for an assessed assignment, you want to spell out the word. I really hesitate to use any sort of abbreviations except for common unit abbreviations. So abbreviating the word max, abbreviating the word absolute as just ABS, okay? Be very hesitant to ever do that, okay? Write out the full words here. I know it seems silly and it's like a hassle, but some grader, okay, from some other part of the country, if they have indigestion the day that they're grading your test, and like, ooh, abs max, what does abs max mean? I don't know. I'm going to take a point off because this is abbreviated, okay? Write out the full words. There's no question in their mind about what you mean, okay? So, anyway, all right, next one. Ooh, this one's not even graphed for us. I guess we better graph it. All right, so let's see here. Let's graph this quadratic here. So, all right, I'm going to try. Let's see. So it switches over 2, so we'll plug 2 in. 2 squared x. You know what? This might be better if I just type in my calculator and use the table. All right, so let's see if I can scoot this up and fit it. So 2x to the third, minus 3x plus 1. I'll go to my table and delete out some of these values here. And so we're going to use 2. And so at 2 I get 11. That is not right. Did I type something in incorrectly? Yeah, 2x to the third. Thank you. Okay. I was like, that's way too big. Okay. So at 2 we get 3 then. So 2, 3, and then what type of circle should I put there? Open, because x is not equal to 2, it's less than 2. So we're going to put an open circle at 2, 3. And then to get more x values for this top piece, what x value should I pick next to kind of plug in? Yeah, 1. We got to go for x values less than 2. So I'll plug in 1. So I get 0. So at 1, it's 0. And then at 0, it's 1. Okay, and then let's see here. At negative 1, it's 6, which is now like off my paper, but I'll put that like that. Okay. And so let's see. I'm going to graph that real quick just to see. I think it goes down below the x-axis. Yeah, just slightly. Okay. So make sure I get that right. Okay, so something like this. Ooh.
I think it's
like that.
Or the point at which it bottoms out.
Yeah.
Is that x equals 3/4?
Okay, 3/4.
Yeah.
Okay, yeah. That's probably right then. Okay. And so there's that little piece. All right. Of it. And then we're going to graph the 7 minus 2x. So if you want to type that one in, you can, just to help you out with the calculation sum. And then we're going to use actually 2 again this time. But 2 is an actual point. So at 2 it's 3. So now we can fill in that dot there. They do connect. And then I'll type in my next x value I can plug in is like 3. So at 3 it's 1. And then actually I can do more because I know my slope's negative 2 here. So it's just down to right 1, down to right 1, down to right 1, down to right 1. So we just connect those dots. Okay. So since those two since the two pieces in our piecewise function joined up, we can say this function is what? Continuous. Might not be differentiable, right? In fact, where isn't it going to be differentiable?
X equals 2.
Yeah, at 2 it's pointy, exactly right. But it's continuous for sure, right? So yeah, in fact, I think you're, Brandon, yeah, I think you're right. It's going to be at 2 that it's not differential because of the pointiness there. But that's not what we're concerned about right now. We're just worried about getting that graph there, okay? And now we want to find our kind of like critical values here. Okay, so it looks like we maybe have a relative minimum on our graph here. All right, so let's see here. So Maya, where does it look like we maybe have a relative minimum? So at 2, 3, that's a relative minimum?
Oh, minimum?
Yeah, minimum.
Well, it would be like the bottom.
Yeah, wherever that bottom is, right? So how can we figure out where that bottom piece is? What can we do here? There's a couple options. So we could graph our we could graph on our calculator, finds the minimum value. That's one way to do it. We also now remember that well, actually, let's just do it that way. Yeah, I like that. That's good. We'll do it that way for now. Okay. So yeah, so let's take that. So 2x to the third minus 3x plus 1, and we'll go to calc minimum. Oh my gosh, I did it again. Okay, so we do have the minimum command on our calculator, folks, in the second trace. Okay, the calculate menu, minimum is there, so we can do that. All right, I'm just going to go to the left of my minimum, go to the right of my minimum, hit enter. So it looks like, now how should I read this number here? 0.7. Yeah, 0.75. Okay, this is a calculator error. Okay, yes, there is this 0.000048. That's an error. It should just be 0.75 and negative 0.125. Okay? So we have a relative minimum then. At x equals 3/4, we'll say. Okay. And we have a relative maximum Relative maximum, where do we have our relative maximum? At what x value?
2.
Yep, 2. X equals 2. Okay. Is this relative maximum, is that relative maximum, is that also an absolute maximum? Is that the highest point? Yeah, no. And then, Maya, is this relative minimum, is that our absolute minimum? Yeah, no. Okay, right, because our function continues both higher and lower than those 2 points. So that's a relative minimum and maximum. Okay. Notice here, f prime of 3/4. Maya, what does it look like the value of the derivative will be at 3/4 there? Yep. Good. And then, Mac, what do you think the value of the derivative at 2 is going to be? Since it's pointy like that, the derivative will be what? Not 0. It's pointy, so that means the left hand is going to suddenly or left hand, you have a positive slope, and it suddenly jumps to a right hand. So the derivative at this pointy piece is undefined. We'll say does not exist. Okay. All right. So, kind of like drawing the conclusions that we've kind of already seen. Ryan's already picked out. Maybe some of you guys have already kind of figured this out. In each of these examples of relative extrema, the derivative is either 0 or undefined or does not exist, whatever you want to say. That's right, you switch it a shot. This is 0 undefined.
I think we calculated it out, and there's a chance of him getting all 4 systems right.
It was
like,
2. Those 3.
Okay. So, that's it for the copies of notes. Now I'd like you guys to get a piece of paper out. We're going to continue here then. Now we're going to actually go into guidelines for how we can now find these relative extrema, how we will be finding them analytically. We've kind of been using graphs and things, but now we're going to use like calculus analysis. Well, we'll do this first, I guess. Oops, that's the wrong page. Okay.
Yeah, I can use the header I made yesterday for notes.
Yes, that's right. You can now use that header.
Also, take low 23, change to low 24.
That's right. Correct dates. Okay. So, now we're going to kind of hash out our steps for finding extrema on an interval. Yikes. Okay, so finding extrema on an interval. All right, so here are our guidelines to follow. This is looks like I have, and this is just for absolute extrema for right now. We're going to worry about absolute extrema. It looks like. Okay. So guidelines for finding absolute extrema. And the guidelines for finding relative extrema are similar, but we'll have to add a little extra step in. So anyway, okay. Oh, on a closed interval. Remember, we really need that closed interval to find absolute extrema. Sometimes you'll still have absolute without the closed interval, but to guarantee that we have absolute maximums or absolute minimums, we need a continuous function on a closed interval. And so that's what we're going to deal with here. Okay. So, given a continuous function f on a closed interval, and I'll say the closed interval is a, b, here's what we're going to do. Step 1. Find the critical numbers of f. in the interval from A to B, the open interval, so we don't include the endpoints here. How do we find critical numbers again?
So the derivative equals 0.
Set the derivative equal to 0, or when the derivative is undefined. So I'll put that little thing right here. It's either f prime of x equals 0, or f prime of x is undefined. Okay? So that's how we do that first. So we find the critical numbers, set the derivative equal to 0, or see when the derivative is undefined. You have to check both things, okay? This is one of those situations where like 80% of the time you only have to worry about when the derivative equals 0. And so some of you, when you get in the habit of seeing something only that 80% of the time, you think that's all you have to check, and then when you see one of these exceptions show up, you forget to also check to see when the derivative is undefined. So don't forget, it's going to be both things, okay? All right, next one. Evaluate f at each critical number. Okay, so if you have a critical number at 1, like maybe 1 makes your derivative 0, or 1 makes your derivative undefined, that's a critical number, 1's a critical number, you plug that 1 back into f then, all right? So we evaluate f at each critical number. We also need to check, besides absolute maximums and minimums occurring between the endpoints, absolute maximums and minimums could also occur at the endpoints, right? Let me see here. Do I have that written here somewhere? Yeah, right here. Remember here, for example, okay, here we had our function on a closed interval. Our absolute minimum occurred between 1 and 2, negative 1 and 2. But our absolute maximum occurred on 2, okay, on the endpoint there. So we have to also check, we have to evaluate f at each endpoint of the interval AB. And I'm not going to, of AB, the closed interval AB there, like that. All right. So you evaluate f at your critical points, evaluate f at your endpoints. All right, and now comes the easy part. It's just the least of these values is the absolute minimum of f, or absolute minimum value of f. Okay, and the greatest of these values is the absolute maximum value of f. Okay? That's it. 4 steps. It's easy as 1, 2, 3, 4. Okay, so let's do an example here. Let's find the absolute extrema of f of x equal to 3x to the 4th minus 4x cubed on the interval there, negative 1 to 2. So let's get a little sketch of this first, just to kind of see what we're dealing with. Alright, so we can use our graphing calculators to help us with this one, just because it's kind of a funky thing. So 3x to the 4th minus 4x cubed Now, if you really want to be slick, because we're not interested in this full graph, right? I'm not interested in the full graph of a function 3x to the fourth minus 4x cubed. I'm only interested on what interval? Negative 1 to 2. So if I want to only view from negative 1 to 2 on my graphing calculator, I can press the window button. And instead of my x min being what it is right now, what should I make it?
1.
Negative 1. It's the lowest x value, right? And what's the highest x? What's my x max? What should that be? 2. And now when I go to graph that, now I can see exactly what my function is going to look like. Now you can see that I'm missing some pieces, so I need to go up a little bit higher, my y max. So you can see that, again, I didn't go up high enough, like I still have some pieces of my graph missing because I'm supposed to go from negative 1 to 2. So if I adjust my y max, let's try like 10 and see what happens. Okay, so that one works over there. Oop, but 10 wasn't quite high enough for this side, so I can see the rest of it. So let's try like 15, see what happens. Pretty close. Let's try 20. I think that should be good enough then, finally, once we get there. Ah, okay, yes. So now I can finally see our full graph there. So I'm going to try and sketch that here. So I have like a point here, and then a point here, and then negative 1's over here. So negative 1, 1, and 2. I didn't do a great job spacing those out very evenly. But it starts like down like that, and it bottoms out at 0, it looks like. And then it goes down till maybe it bottoms out at 1, and it looks like it hits up like that. Okay. So something like that. Okay, just a quick sketch, nothing like too crazy there. Right? So take a look at that real quick, and let's just predict where we might have some critical points here. Remember, critical points are where the derivative equals what? 0, or when it's undefined. So let's just take a look at our interval right here. Okay, again, these are our endpoints. I'll put like little filled-in circles there. Just take a look at it real quick and see if you can predict either your sketch or your graph on the calculator there. See if you can just predict by looking at it where you think we're going to have critical points. I'm going to call on someone. Okay, so let's go to. Oh, okay. So Connor, you showed up again. So yeah. So where do you think we might have a critical point here? At what x value? Where does it look like the derivative of this might be 0?
Coming in the graph with -1.
Negative 1 will have a graph of the derivative is going to be 0 there.
Oh, there. I thought you were talking around 2.
Around 2, the slope is going to be 0.
Oh, I thought you were asking about the point.
No, I'm talking about the little piece of the graph I have right here. This is f. Where does it look like the derivative will be 0 of this function?
It's going to be 0 at 1.
At the x value of 1, it looks like it does bottom out there. So, yep. Do we see any other ones, possibly, where the derivative might be 0?
Well, maybe at 0.
Maybe it's 0, right? Maybe it's like the cubic where it kind of flattens out but then still continues to decrease. So we'll see. Let's see. So how can we actually see when the derivative equals 0? What should we do? Take the derivative and set it equal to 0. That's right. So that's why taking those derivatives, guys, so important in the previous unit, because now we're going to be using the derivative to then do more work. So if you make mistakes in taking the derivative, guess what? You won't be able to find absolute extrema, okay? So you're going to be screwed. So that's why we need to really make sure we have those rules down. Okay, so the derivative here is 12x to the third minus 12x squared. All right, and we set that equal to 0. So 0 equals 12x cubed minus 12x squared. And by the way, guys, writing f prime of x equals this is important. Just writing 12x cubed minus 12x squared and then maybe setting equal to 0 down here, that's not really good math. You need to be putting f prime of x equals 12x cubed minus 12x squared. Then you need to be put a 0 equals 12x cubed minus 12x squared. This is part of your explanation, okay? If you're leaving out f prime of x equals this and 0 equals this, it's like you're writing with incomplete sentences, okay? It's like going into English class and like writing with incomplete sentences, okay? It's like saying, you know, the red ball. Okay, what about the red ball, you know, or something like that. You need to make sure you're putting these pieces. They're important. Okay. So now that we have this equal to 0, we can say, okay, so I don't need to rewrite the 0, I can continue to write the equal sign here. What can we do to start solving this? Yes, factor. So Emma, what factors here? 12x squared factors, and then what are we left with? X minus 1. And since this is equal to 0, right, if it was equal to any other number, we can't do this, but since it's equal to 0, what can we do, Emma? Yep, 12x squared then must be 0, or x minus 1 must equal 0. In this case, divide both sides by 12, square root both sides, you get x is 0. And then this is x equals 1. And sure enough then, do we have a critical number at 0? Yes. Do we have a critical number at 1? Yes. Okay. So, number 1, we did that. We found the critical numbers of f in AB. We only check when f prime of x equals 0, but will this thing be undefined?
Never.
Yeah, there's no denominator to worry about or anything like that, so you don't have to worry about that. Okay. Number 2. Number 2 says evaluate f at each critical number. So that means I have to find f of what?
F of 1 and f of 0.
1 and f of 0. All right, since I already have something in my calculator, I'm just going to do it that way. So I'll go, let's see, yep, still typed in there. So I'll type in 0. So at 0, it's 0. And at 1, it's negative 1.
So these aren't typically calculator problems, though, correct? Or are they?
Sometimes they are. Sometimes they're not, though, yeah. So you just, again, it's just evaluating it, though. You just find what is f of negative 1, what is f of 0. All right, so there we evaluated f at each critical number. And now step 3, evaluate f at each endpoint. So that means f of negative 1 and f of 2. Okay, and again, since we have our calculators here, let's just do it that way. So I get 7 and I get 16. So now,
wait, why do we evaluate the number at each endpoint, the function at each endpoint?
because those could also be the highest or lowest points of our function. If we're trying to find the absolute maximums or absolute minimums, those could be the highest or lowest points. Relative max, relative mins will never occur at endpoints like that.
Okay, but if it's on an interval, like
if it's on an interval and we're talking about absolute extrema, we need to include those. We need to include those endpoints. So now that we have all that analysis set up, by the way, guys, these are all candidates for absolute maximums and absolute minimums. We have not yet identified the absolute maximum min. That's what we're supposed to do. Number 4, the least of these values is the absolute minimum. The greatest of these values is the absolute maximum. So that means then, Caleb? No, you don't answer it? Okay. Donovan, what is the absolute minimum value here that we got? From these candidates, what's the lowest value that we got? -1. So this is the absolute minimum. Yep. I'm off the screen.
When you use your table, what did you plug in here?
Oh, sorry. Hold on. Let me finish writing this. So absolute minimum of f is at the point 1, -1. Okay? This is very helpful. And writing this little sentence out, that's a very good idea. You're telling the person, okay, the absolute minimum of the function f, right, because we did also talk about the derivative in here, so that's why we want to specify of f is at the point 1, -1. This way you don't have to worry about, wait, are they asking for the absolute minimum value, or are they asking just for the location, and getting the x and the y's mixed up? If you just give the coordinates, you got the whole thing covered. So that's why I recommend just give them the coordinate. All right, sorry, back to you, Tyler, real quick.
What's your y equals? Oh, so you plug in the original, not the derivative.
Yes, exactly. Again, look, I'm evaluating these. You see no primes there, right? No primes. Yes, and so that's why it's very important you understand we are evaluating back in the derivative, because what are we finding here? We are finding the absolute extrema of f. So we should be plugging these back into f. Plugging back into f. Okay, Donovan, what's the absolute maximum value here? At 2, it's 16. So yeah, so absolute maximum of f is at the point 2, 16. Okay, yes.
What if you have two of the same value? Like, what if you have two?
So then you would say both of those are absolute maximums. Okay.
So on a test when it's asking for the absolute values, do you want it in like interval notation, so like 216, or just like x equals 2?
Well, interpretation is
Say that one more time when they're looking for what?
point.
Like the absolute values, would you want on a test? Would you want us to rate it as like x equals 2, or
It's a coordinate. So
you want
two.
it? So you want it as a coordinate?
Give it, yeah. In general, it's a good idea to give the coordinate because, so for example, there's kind of two different ways you can be asked about absolute extrema. You can be asked, where does the absolute maximum occur? That is an x value.
Okay.
That's all you have to give.
Okay.
You also could be asked, though, what is the absolute maximum value? Maximum value, that is the y value at the absolute maximum. So, how do you fix that? Just give the coordinate of the absolute maximum, or the coordinate of the absolute minimum. That covers your bases.
So
It's
just
both the x
always-
and the y coordinate.
So you can never go wrong, right?
If you write the coordinate right, exactly. Unless sometimes there'll be situations maybe where you can't get one or the other, so then you just would give what you got. Okay, Brandon, and then Austin.
Does these kind of lead themselves to like rapid fire? Like what is the absolute max, what is the absolute min, what is the relative min, what's the relative max?
It depends. I mean,
Critical points, like all that.
that's stuff that we're going to be doing. Pretty quickly. I mean, not like I'm going to like give you a 60-second timed quiz. You're like, oh my gosh, kind of thing. But I mean, yeah, this should be like pretty. The process will become fairly rote, I would say. Like very, it's like, all right, find the relative max, and you guys are like, okay, take the derivative, so it equals 0. Oh, and also when it's undefined, get your critical points. You'll analyze those critical points and the endpoints.
So with that, like, since we know it's going to be 0, fine, if we clearly can see that it goes to the point, do we have to show our work then?
You should still be able to justify why there's a critical point there. For example, the pointy stuff, and you want to say obviously more than just it's pointy. You want to say the derivative would suddenly change from either like positive to negative, not a smooth transition. The derivative would jump, suddenly, so it's not going to be defined at that point. So yeah.
Are these problems typically accompanied by a graph, or do they usually just come with an equation?
So I like to draw the graph right now, just so we can kind of like get that connection, because sometimes you'll be given a graph, and that's all you'll be given. Sometimes you'll be given the function, that's all you'll be given. So I want you to be comfortable with both. All right, next one. And this one I want you guys to try on your own. Find the absolute extrema of f of x equal to 2x minus 2x to the 2/3 on the interval -1, 3. Excuse me, if you want it like a graph, you can. -1 to 3. Sorry, it's like, oh, I see what you're saying. Yeah, x to the 2/3 power. Okay, on the interval from -1 to 3. So go ahead and give that a shot.
I think it's funny, like the harder the graph function is, the longer it takes my calculator to figure out what.
Yeah, it's so funny. They need to update the operating systems for those calculators. Is that right? Definitely since I've been in, so the 90s at least. So it's like 20 years old.
Looking at that chip thing.
No. So if you want to use a graph here, you may. If you want to just hop right into, our guidelines there, that's fine as well. But again, this thing kind of follows the same procedure we've seen before, right? It's like, what do we do when we're given something in calculus? Take the derivative, okay? Yeah. Right, no, yep, keep going. That's important though, you wanna convince yourself that it does continue to go and doesn't like, turn around. But also understand you're also on a particular interval. So that's what you really need to worry about is from -1 to 3. That's your universe. Your universe is from -1 to 3 here.
Hey, to cancel 1/3 on this side, you would just cube 2, right?
Yeah. But you first have to, well no, because that's really negative 5, negative 1/3.
So for a problem like this,
Yes.
we just switch the numerator to 0 and the denominator to 0. If we combine, or somehow combine it.
Oh.
You don't necessarily, well, I guess you said equal to 0.
Wow.
2
Wow.
divided by
So,
1/3.
there's a couple ways we can solve that, I guess.
1.5.
You can have a common denominator, yeah, you want to do it that way.
I'm gonna put the numerator in, numerator equal to 0, and that's like 0, and
Yep.
the denominator.
Yep, exactly.
3 point. Graph.
I'm gonna multiply 2 over 2, 3 over 3.
Mr. Wood.
Yes.
4 over
How do, so, to find the 0 of this, so I took the derivative, now I'm trying, so I set it equal to 0.
You girls are done your problem, right?
So I set it equal to 0, and then I subtracted the 2 to get rid of it.
So multiply both sides by -3/4, I guess I would say.
Yeah, and then to get rid of the negative 1/3, would I just...
You can make it just reciprocal both sides if you wanted to, because the -1/3 is 1 over the cube root of x, so just reciprocal both sides and then.
Oh, so just do -3, just take the negative cube root, or not the cube root, the negative.
I got a common
cube.
denominator.
Can I just put the derivative in our calculator and
Yeah,
then
that's
like...
right.
So we get kind of ugly fractions.
Yes, you do get some nasty
Okay.
fractions. What's that look like?
More.
So,
So I got a
x
common
to the negative
denominator.
1/3 is
Like
the
my
same as
derivative
1
is one big
over
fraction.
x to the 1/3,
And
right?
I set the numerator equal to 0,
Like-
and then the denominator equal to 0.
That's equal to 1 over x to the 1.
Yeah, but you can't do that.
3/2 equals 1 over x to the 1/3, that means
6 times the cube root of x minus 4 over 3 times the cube root of
both
x.
sides, and then cube equals 2, right?
No, it should be 2 minus 4 over 3.
No, because when you get the derivative of 2x or 2/3, it changes.
I know.
Bring it up front and then you get times 2.
The other extreme.
Yeah, you have 2 minus 4/3
No,
x.
8/3. Or 4/3 by 2.
2 times 2 is not 8.
Yeah.
Which is negative 4.
So then you multiply by the power 2/3.
2 times 2 is not 8. 2 times 2 is 4.
You might as well do that.
You have to write. Which is you just multiply that out. Throw it up by 1.
Oh man, Mr. Wood, why did you give us one of those disgusting fractions? Not cool.
Oh, poo.
My sentence missed exactly.
It is a different way to do it.
Yeah, you keep the derivative both sides. Because it's 2.
Yeah, I should do it that way.
So,
No, because
Hang on a second. 2 minus... Oh, for my derivative? 2 minus 4/3 x to the negative 1/3. 2 minus 4 is...
How'd you type it in?
-2.
That should be how you typed it in. Oh, okay. You're right. Sorry. Okay. You guys are doing 2, right? Never mind. You have a 2 there, right? Okay, that's right. Never mind. Thank you. I made a mistake from what I wrote earlier. Never mind. It's just a word.
So your derivative is still correct.
Yeah. Sorry, I made a mistake. Yes, it was. Okay. Sorry. That's what the graph looks like then, yes? Okay, I copied the problem down wrong from what I had on my notes that I wanted to do. But this still will work fine. Just not as nice as the other. That's why the numbers worked out a little bit funkier. So, all right.
When you did the chain rule,
The derivative here?
yeah.
The derivative of 2x is 2. The derivative of 2x to the 2/3, the 2/3 multiplies out front, so it's 2 times 2/3, negative 4/3, and then you lower the power by 1. 2/3 minus 1 is negative 1/3.
Then don't you want, like, multiply the one inside?
What's inside is x.
No.
The 2x is not being raised to the 2/3 power, it's just the x being raised to the 2. If it was 2x being raised to the 2/3 power, you have parentheses around it.
Oh, see, for some reason I put parentheses around it myself.
That'll do it. Over 27, yeah, is what that should be for that one of your critical points. Okay. But then also f prime is undefined when x is what? What x value makes f prime undefined here, folks? 0. So you also need to, 0 is also a critical point. Okay, so we're going to do f of 8/27. We'll do f of 0. We'll do f of negative 1, and we'll do f of 3. Don't forget, we also got to check all those endpoints as well. Both endpoints, I should say, not all of them, but both of them. Okay, I'm going to use my calculator here to just do this quickly. So, second trace, I'm going to do the value command, and I'm going to type in 8/27 for the first one. And 8/27 gives me approximately negative 8/27 is what it looks like it gives me. Exactly. Okay. Second calc value at 0. 0. Okay. Second calc value at negative 1. Negative 4. And second calc value at 3. 1.8398. Woof. That's a mess. Okay. So we'll round that to 1.840. And I'll give that as approximate. A little squiggly equal sign for approximately equal to. Question?
How did you know to do f of 0?
Because 0 makes my function makes my derivative undefined.
You just have to look at the problem and do that.
Well, because x to the negative 1/3, like if I rewrote this derivative here, bless you, it's 2 minus 4 over 3x to the positive 1/3, right? X in the denominator, what value would make it 0? Or what value would make the denominator 0? 0 would make that denominator 0. You set your denominator equal to 0. Even though there's a 2 here, like a nice 2 that would never have any problems, if this is a problem, the whole thing is undefined. If this is undefined, the whole thing's undefined. Okay, you could also get a common denominator, combine like terms that way and stuff too, but really we can just see right away 0 is going to make that thing undefined. Okay, so the absolute maximum. of f occurs at what point? 3, comma, yeah, like approximately 1.840, we'll say. And then the absolute minimum occurs,
In negative 1.
yeah, occurs at -1, -4. Our absolute minimum of f occurs at -1, -4. Okay? There it is.
Unfair problem.
Okay, pretty ugly. But again, that's why it's so important to know those fundamentals. The fundamentals will at least help guide you, because, yes, sometimes the derivatives can be a little bit messy.